Okay, the last speaker this morning is Paulo Zato Rodriguez, who's going to talk about an efficient and general method to compute steady vortices without symmetry in unbounded flow.
Thank you. So my name is Paulo Zato Rodriguez. I'm at HUI, but I should say this is some work I did with Charles Williamson during my PhD at Cornell. And as it was mentioned, this is on developing an efficient and general method to compute steady vortices, possibly without symmetry in unbounded flow. And to set the key ideas, it is well known that there is a correspondence between steady states of the Euler equations and extreme of energy under isovortical perturbations. And it's not necessary to say this here, but one property of isovortical perturbations is that you can take any arbitrary contour that moves with the fluid, and the circulation around this contour is going to be preserved by the perturbation. So it's also topology preserving. So you can use this variational principle to seek steady states, essentially by using relaxation approaches which seek extreme of the energy or some analogous of the energy. For example, there is the magnetic relaxation approach, which, to the best of my knowledge, has been implemented for bounded or periodic flows. Another method is the simulated annealing procedure, which also, as far as I've been able to find out, has only been implemented for two-dimensional doubly periodic flows. Now, this is to say that here we take a slightly different approach. We try directly to solve the steady Euler equation, and we're still looking for solutions corresponding to isovortical rearrangements. We look just at 2D problems for simplicity. But a key difference here is that we're looking at an unbounded domain. And a key point is that we're looking for families of solutions. So just to clarify, by a steady flow, we mean a flow that's steady in a frame of reference that's moving. So for example, for a vortex pair, you have to look at things in a rotating reference frame. So in 2 dimensions, you can write down the vorticity equation in this way, where this u move is the fluid velocity in the moving frame. And then a steady state just corresponds to this being 0. And the very simple intuitive physical interpretation this has is that each of these vortices is not deformed as it moves through the flow. So you could come up with a naive sort of solution approach, saying, okay, I could guess some shape for the vorticity distribution and some velocity for the moving frame. Then I could invert the vorticity to get the velocity from Biot-Savart. And then I could evaluate the steady Euler equation. And if my residual is small enough, then I have a steady solution. If not, I can have some way of fiddling with my guess, for example, by Newton iteration, and then you can keep going. But it turns out that if you're seeking general solutions in an unbounded fluid, this procedure in general will not converge. And an issue that you encounter is that if you have that particular vortex is a solution, then you can translate the vortex or rotate it or rescale it, and you get some neighboring trivial solutions. Now, these are trivial, but still they will show up as 0 eigenvalues in your Jacobian if, for example, you're doing things with a Newton iteration kind of approach. And so your iteration will fail to converge. Now, what brought us to this problem is that we've been working on this approach where one can plot velocity and impulse for families of steady states, and this can tell you something about change of stability in your fluid flow. And a key requirement for this approach to work is that your family of solutions must be constructed from isovortical rearrangements. And everyone here knows that one way of looking at this is that all flows in this family must have the same Casimir invariance. And one intuitive way of thinking about this is that it's a way of constraining the shape of the vorticity distribution, for example. So past work has used different ideas to try to get around this issue involving degeneracies. One idea involves assuming some specific functional relation between vorticity and string function in the vortex cores. Another idea involves assuming a specific outer shape for the edge of the vorticity distribution. This recent working work of Elkrat used a single value decomposition to modify the Jacobian. And I should also explain that all of these approaches have also assumed the solution had certain symmetries to be able to get convergence. And to the best of my knowledge, these approaches cannot give you non-symmetric vortices with prescribed Casimirs. So the very simple question here is, well, is there some simple way that we can ensure convergence and prescribe the Casimirs at the same time? So for simplicity, we just use a vortex patch discretization. So you just represent the vortex through a stack of uniform vorticity regions. And a nice thing about this is that if you fix the area and the vorticity of each region, that fixes all the Casimirs. And now we'd like to prescribe the centroid of area of the vortices because that fixes translation. We also thought we could try to prescribe the cross product of inertia of the shape because that would fix the rotation. And we actually realized that Morrison used this idea in some of his work. And then we also like to fix the area of each vortex patch because that fixes the Casimirs and it also fixes the scale. So we'd like to apply all of these constraints to the problem, but the question is, well, how? And so we're looking at this steady vorticity equation, which for a vortex patch just tells you that there must be no fluid velocity normal to the boundary of the patch. So you can write it as a function along the perimeter of the vortex. And then we have a bunch of constraints we want to enforce. And we use this idea initially introduced by Chen and Safman for steep gravity waves, which involves essentially appending these constraints to the original equation by first multiplying them by some arbitrary function, in this case, for example, the arc length around the patch, and adding and then setting that to 0. And I won't explain this in detail here, but the point is you can argue that these can be used to solve the original steady vorticity equation subject to the constraints. So before we can go ahead and compute the steady states, there is another issue that we need to address, which is that as you compute these families of steady states, eventually you can get that some very fine scales can form. And the first to notice this were Diem and Zabusky. They were looking at these steady vortex states that have some azimuthal symmetry. So they used cylindrical polars to look at the solution and wrote down a Fourier expansion for the radius. And the point is that they noticed that eventually corners would form, and you have to keep adding nodes, and eventually the computation becomes too expensive. Now, of course, today you could just go to a very big computer and go very far along this family of solutions, but the point is this is a very simple problem. You're just looking at uniform vortices. You shouldn't have to go and use a supercomputer to try to tackle this. So Safman and Zito proposed a way to get around this issue by introducing this rescaled coordinate to build your Fourier series. And the point is you build this map that defines your coordinate so that you concentrate more resolution in regions where you expect corners to develop. And the problem with this is that in general, you don't know where corners are going to develop. So this is not a very general approach. Now, more recently, Elkrat's group came up with this idea where, given a certain guess for the boundary shape, they would only compute the correction normal to the boundary. And then they expanded this in a Fourier series in terms of the arc length around a patch. And this is very general, and it's much better than just using cylindrical polars. But the problem is that eventually you do get the corners form, and the computation does ultimately become too expensive. This is how far they were able to get in this problem. So the very simple question now is, well, is there some simple way we can make calculations more affordable? And to fix the ideas, you can look at the neighborhood of a stagnation point in a pure strain flow. And suppose that in general, the highest curvature streamlines in a flow will occur near stagnation points. So this suggests that you should take maybe a little length along a streamline and stretch it by the inverse of the local fluid velocity. And just to remind ourselves, you're in the moving frame. So then you can build a map like this. And some reasons why we like this is that this is very robust, because even if you have some small errors in your boundary shape, you're obtaining u from an integral over the boundary shape, and that will smooth out small errors. And it's also cheap because you already have the fluid velocity everywhere as a byproduct of your iteration, your solution procedure. And I must mention that a different interpretation of this coordinate, this coordinate, is that this is a travel time along a streamline in a steady flow. And Dritchell in '95 was working on a stability analysis for steady vortex patches, and he found that using this kind of travel time parameterization to write down his eigenmodes allowed him to get very fast convergence in the series used to write down the modes. But to the best of my knowledge, this is the first time that this kind of idea has been used to compute steady states in an unbounded flow. So just to summarize, we'd like to remove degeneracies while prescribing this Casimir invariance, and also while allowing for non-symmetric solutions. And we do this by using this modified steady vorticity equation. At the same time, we also want to handle these issues with boundary resolution. And we do this by introducing this inverse velocity mapping for computing these steady flows. Without getting into the details of this, we discretize this with a Galerkin method, and then we convert to a solution using a Newton iteration. Now, the key question is, well, does this work? And is this any better than other methods that are out there? And I could show you a side-by-side comparison with other methods, but that's not the most exciting thing to look at in a talk. So we put that in this paper, and I'll just show you a quick example in this talk. So let me introduce this example a little bit. This is a family of elliptical vortices. These were discovered and described analytically first by Kirchhoff in 1876. Here we're plotting this solution family in terms of its velocity, angular velocity of these ellipses, and the impulse that these ellipses have. In 1894, the British mathematician A.E.H. Love did a stability analysis for this flow, and he found that there is a bunch of bifurcations that you can find on this family of solutions. This is the first bifurcation you encounter as you start from a circular vortex and you make it more and more elliptical.
Are these dates on the horizontal axis?
Yeah. They could be right. No, they're not. Before and after, yes. So the first to compute the bifurcated family for this bifurcation was a student of Safman, James Cam. He used a certain kind of accuracy to look at the solutions. And this is how far he could get. Eventually, you see these fine scale details forming. Now, we look at this problem again using this method, using a higher resolution, and we can go all the way to the end of the solution family. And just for comparison, we also computed this using a uniform arc length discretization with the same level of accuracy, and this is how far you can get. And you can see that you develop what looks like a corner here on the vortex boundary. And we're just wondering, well, what happens very close to this limiting state? So you can put a box around that, and then what we did is, well, let's blow up this dot representing the limiting state, and you can make it transparent, and you see there is some just barely visible little feature in there. And you can put the box around that again and then zoom in again so that this fills up the screen, and you see what looks like a turning point in impulse. And the funny thing is that this now, this plot fits within the line thickness of the first plot I showed you. And incidentally, from this stability approach I mentioned, you can work out that you have a loss of stability as you go around this turning point. Well, at this point, we're curious, what happens if you go even closer to this limiting state and you blow that up again? Well, you get another turning point, and now you're at a magnification of about 100 million from the first plot I showed you, but still you're only using about 700 normal modes to look at this problem. So this is still something you can do on your laptop if you want to. And so it looks like you have a velocity impulse spiral as you approach these limiting states. And of course, we're curious what happens if you go even closer. But now here you're quite close to the machine precision, so we didn't go any further. So I should mention that we use this numerical approach to explore existing families of solutions in detail. These are the limiting states for the first three bifurcations from the ellipse families, from the elliptical vortices. We also looked at other isolated flows, and you can also look at spatially periodic flows. This is what you get from a Kármán street if you replace it with finite area vortices. We can also compute families of solutions that have lower symmetry. These are some vortex pairs, and this is what you can get for the Kármán street. And an intriguing thing is that all of these families of solutions seem to eventually exhibit these velocity impulse spirals, at least to machine precision. And just before I wrap up, I should mention that if you're looking for steady, non-symmetric vortices in an unbounded flow, well, the first point vortex equilibrium involving equal strength point vortices that were non-symmetric were first found by RF and Baintain relatively recently, in '98. To the best of our knowledge, this is the first case involving non-singular vortices with no symmetry in an unbounded flow. And we also found a bunch of other flows like I showed you earlier, but these still have some symmetry. So just to conclude, we worked on this and developed this computational approach for steady vortices. The two key ideas here are this modified steady vorticity equation and this inverse velocity mapping discretization. And this construction allows you to compute families of solutions that have prescribed Casimirs, so we can build these bifurcation diagrams. They're relatively cheap to compute, and you can also compute lower symmetry vortices. And we're able to find these velocity impulse spirals, which you can follow at least down to machine precision. And I should mention, since we're using a Newton iteration kind of approach, you can just turn off your constraints if you want to. And then you can look at the eigenvalues of the Jacobian, and you can get eigenvalues for the stability problem. And you can also nest a bunch of vortex patches to get more realistic vortex flows and then compute their existence and stability. This comes out if you look at a family based on the Chaplygin-Lamb dipole. This is in a very recent paper that just came out. And I should mention that this kind of discretization also works for other problems where you have sharp interfaces. For example, we played a little bit with surface gravity waves. Thank you for your attention.
Thank you very much. Are there any questions or comments? If not, then let's just thank all these morning speakers